So, yeah. Okay. So we looked at covalent bonds. And so what I would like to add on is that, of course, covalent bonds, you're going to get two types. Okay. You're going to get the non-polar covalent bonds, like you see for this case for hydrogen molecule, where, yes. Oh, okay. Okay. Okay, yeah, I'm now hoping that you're able to see that I had not yet shared the screen. Thank you for that. Oh yeah, so there we're talking about covalent bonds, right? So covalent bonds, they can either be what? They can either be covalent or non-covalent. So remember, it goes back to what we talked about, electronegativity, right? So if two atoms which are forming a covalent bond, they are what's this? Their electronegativities are not too different from them. So the difference in their electronegativities are not, or rather, is not large enough. Then what's going to happen is that the electrons are going to be fairly shared. Okay, so if they're fairly shared, then you're not going to have that polarity that we were seeing in molecules such as water and things like that. Okay, so those are the two examples. So there you see the hydrogen molecule, it's a non-covalent bond. Of course, it's the same atoms, so the same electronegativity, so the difference is zero. Now, even for carbon, you see carbon and hydrogen, their electronegativities are very, very near, are close, isn't it? Oh yeah, so their difference won't be a big number. Therefore, as a result, when electrons are shared in these atoms that we are seeing, sorry, in these bonds that we are seeing, they are going to be shared so fairly, in such a way that we could say that there won't be any polarity. So what this simply means is that these electrons are going to be shared, rather they are going to be shared equally, so much that there won't be any atom which will be slightly positive or slightly negative. Okay, since the electrons are almost halfway. It's, you can think of it like you're trying to grab something. Let's say you're trying to grab something from your friend's hands, or like snatch something from your friend's hands. You know, that friend of yours, if you've got the same strength, you find that it will be very hard, and what will happen is that you end up maybe ripping apart that particular thing that you are trying to snatch from them, isn't it? So at the end of the day, you are both going to have equal. But if in the second scenario, like I said yesterday, you want to grab something from a child or from someone way younger than you, what's going to happen in that particular scenario is that what's this, you easily grab it. Okay, so you grabbing it means that you are more electronegative. Okay, if we consider whatever you're trying to grab to be the shared electrons, isn't it? So that means that you are more electronegative, and because you are more electronegative, therefore you've managed to grab that particular thing from that child. And so because you've grabbed that thing, meaning that you have that thing, you have whatever you've grabbed, and that child doesn't have anything, right? So that's the key thing. So because oxygen has got a higher electronegativity than hydrogen, the difference is quite considerable. So what's going to happen is that you know the oxygen atom is going to be what? The oxygen atom is going to have a slightly negative charge, whereas the hydrogen is going to have a slightly positive charge. So that's something that we talked about yesterday, but I just wanted to make mention of it. Huh? Yeah, so we talked about that. We talked about that. Okay, great. So yeah, so that's basically what they're trying to explain there about electronegativity. Of course, it's explained better in chemistry. That's why you do the calculations, to separate, to find the difference. But for biology, just knowing, that oxygen, nitrogen, these atoms have got what? Have got high electronegativities. But one thing that's important here is it's oxygen, because remember all this is being taught so that you can understand the shape of water and why water has got some of the properties that it has. Okay, so we talked about the hydrogen bonds. So of course these are weak bonds, but together they are very strong. You can think of it as that thing where it's easy for an adult to overpower a child that's alone, but whereas an adult can actually be overpowered by by a large group of small children, right? So that's the thing with the hydrogen bonds. One on one, they are not very strong, but acting together, they are what? They are very, very strong. And that's why water has got all those properties that we talk about, such as adhesion, cohesion, high melting, boiling point, all those things, right? So something that I mentioned yesterday was also about the hydrogen atom bond cannot be formed between more than four water molecules. So that's why I was saying each water molecule is going to be surrounded by how many? By four other water molecules, right? So they love that for a multiple choice question. And then one thing you want to take note of is that angle between that angulation. We know from chemistry that the shape of water is what is V-shaped, isn't it? And we can appreciate that angle of 109 degrees, isn't it? So it's good to appreciate that. You can be asked. So again, that just shows that you can have hydrogen bonds between ammonia and water. That's something that we discussed yesterday. So I just wanted just to for us to run through this. So yeah, so that's basically about it. And then after this, we went to talk about water, where we explained all those changes in states. We talked about the arrangement of water. So the angle can be from 105 to 109. Yeah, so there's that range. Yeah, okay. So properties of water. So we talked about the ability to form hydrogen bonds. We talked about it being being called the universal solvent, and I explained why. Because the polar substances are able to dissolve in water. Why? Because you remember polar like dissolves like, isn't it? So if something is polar, it's going to be dissolved in water because water is polar. Okay, then ionic. This is where I explained how the water molecules are going to arrange themselves around the positive and negative ions. And so, yeah, so this is what I was talking about yesterday. So I explained in detail yesterday, but I just wanted you to appreciate. So you see, because the chloride ion is negative, so which parts of water are interacting closely with this ion? It's the what? It's those positive hydrogens, okay? So remember, it's opposite things are the ones that attract, right? So you don't expect the oxygen part of the water to interact with a negative ion. That wouldn't happen, right? So that's something that you would want uh to take note of from there, right? So yeah, so that's really really about it. Then what else? Yeah, so that's really really something that and I said usually Dr. Shatta wants to test your understanding. So it will bring something like that. Then maybe maybe these ones will be okay. Then just put one where it's the oxygen that's facing the chloride. Then yeah, and then ask you to choose which is the correct arrangement of water molecules around a negative ion, such as that of what? Such as that of the chloride ion, as we have as an example. Then the reverse is true. You see that here we've got the sodium ion, which is positive. So what you are seeing that is the negative part of water, which is what? Which is now interacting. So I talked about it yesterday, but I just thought these graphical presentations would make it easy. Okay, so pretty much we did what we've talked about so far yesterday, but I thought it would be good just for us to review something. So, water is a liquid at room temperature. So you might think that's understandable, but it's actually a shocking truth, because there are many molecules which have got the formula of water, but you find that most of them are going to be what? Most of them are going to be gaseous. Let's take for instance look at those particular, look at hydrogen sulfide, for instance. You've got the same molecule, or rather, you've got similar chemical formula, isn't it? You see, there is H2H2 and HO. So you see, oxygen and sulfur, they are in the same group, isn't it? There's the group six, isn't it? But why is it that same hydrogen, sulfur, oxygen. But why is it that water is a liquid and hydrogen sulfide is a gas? Now that's really, really interesting. And so this is because of the principle of what of hydrogen bonding. So you cannot talk about the special properties of water without talking about the how the hydrogen bonding, because all these things occur because of what? Because of the hydrogen bond. So something that we've already talked about that I emphasized today and also yesterday was that one water molecule can form hydrogen bonds with up to four other water molecules. And I even showed you a schematic diagram some minutes ago, and I did the same yesterday. So yeah, so the fact that water is a liquid at room temperature, that's very, very amazing, because many compounds, as we could see from hydrogen sulfide, they are very similar to water. But you see that it's a gas at room temperature. So water being a liquid at room temperature, it's as a result, of course, of having a high boiling point, which is, of course, is attributed to what? Is attributed to the hydrogen bond. Okay, so that's something that's important to take note of. So hydrogen sulfide has weak forces of attraction between its protons and electrons of hydrogen atoms. So it does not form hydrogen bonds. So hydrogen sulfide doesn't have what? Doesn't have hydrogen bonds. And because it doesn't have hydrogen bonds, meaning when you start to heat the hydrogen sulfide, or when you expose it to a temperature which is relatively high, there are no hydrogen bonds to keep the molecules together. Remember, what's the difference between a gas and a liquid? It's just the distance between the what? Between the molecules, isn't it? So in a gas, you're going to have a what? A larger distance, right? But in a liquid, you're going to have a relatively smaller distance, right? So it is because of that, that a liquid, has got smaller distances between the what? Between the molecules, whereas for a gaseous, you're going to have a what? You're going to have a larger distance between the molecules. So what makes the difference? The game changer is the what? Is the hydrogen bonds. So water has got hydrogen bonds, so meaning the interactions which are happening or rather amongst the water molecules, it's not just the water molecules alone, but they are also hydrogen bonds. So their attractions are what? Are stronger than normal. And because they are stronger than normal, breaking those hydrogen bonds requires more what? More energy. And the more you require more energy, for us, we are seeing it as the what? As the high boiling point. So if it's got a high boiling point, meaning for a very large range of what? Of temperature, is going to be a what? It's going to be a liquid. Okay, so that's about it. So of course, this point really, really marries with the point that we'll now talk about. The next point, which is that the fact that water has a high melting and boiling point. So just to give you an idea uh, of why this is an important fact, is just look at the substances that we have on that table. You will see that water actually has a relatively low molecular mass, and you find that hydrogen sulfide, which has got a larger molecular mass, is actually gaseous. Okay, at 25 degrees Celsius, which is quite interesting, because you would expect something with a larger molecular mass at least to be what? To be a liquid. Okay, so and you see carbon monoxide, you see methane, you see ammonia, they are all gases. Look at the differences in the melting point: -85, -199. Now look at for water, 0. And you can just look at the difference between -85 and what? And 0. That's positive 85 what? Degrees difference. So we see that that's a very, very huge margin. Then of course the same for the boiling point. You see that for the others, they are what? They are in negatives. They are in negatives. but water is actually not just a positive but a very, very large positive, okay, which is 100 degrees, right, degrees Celsius to say. And then you see that now you're looking at the range, in which range, temperature range, is it a liquid. So you look at those ranges, and then you get to appreciate that really indeed water is a very interesting and amazing uh, substance. Now remember, the purpose of you being introduced to all these things in your biology, it's so that you can get to appreciate water as the what? As where all life starts from, isn't it? Remember, that was something that we discussed yesterday to say all life starts from what? All life starts from water. Okay, so that's something important to take note of. So already from the table, we've been able to appreciate the different melting and boiling points of substances. So the reason why water has got all the high melting point and boiling point is, of course, as a result of strong forces of attractions, which are the what, or rather, the strong forces of attraction between the water molecules, which are what, again, the hydrogen bond. So remember, all these special properties that water has, it's because of the what? Because of the hydrogen what? Because of the hydrogen bonds. Okay. So these are very, very important. So now one thing that is important to take note of now, how why does water have these high melting and boiling points? So here's the catch. For substances which only have weak forces of attraction between the molecules, these they boil and melt at much lower temperatures because less energy is needed to overcome the weak forces between the molecules. So here's the thing. If we look at, for instance, hydrogen sulfide, there are no hydrogen bonds between the hydrogen sulfide molecule. So meaning, when you just put in energy to increase the distance between these molecules, by them gaining energy, and then they begin to move around, and then they become gaseous. All the energy that you are putting in goes into the separation of what, of those molecules. But then for something that has got hydrogen bonds, what actually happens is that part of the energy which you are putting in goes into what? Goes into breaking the hydrogen bonds. Okay? So if for instance, and I'm not saying for instance, if for instance just breaking, let's say, or rather separating the water molecules into gaseous would take maybe, let's say, 40 degrees, okay, and then that extra energy to break the hydrogen bonds is like 60 degrees Celsius, right? So it means that the total boiling point becomes what? Becomes 100 degrees Celsius. So it's that thing, right, where there's going to be extra energy which has to go into the breaking of the what? Into the breaking of the hydrogen bonds. So now, as these hydrogen bonds are broken, what's then going to happen is, then there's going to be a change of what? A change of state. Okay, of course, from solid, or sorry, from solid to liquid, or it could be from liquid to what? To gaseous state, right? So that's really about it. Yeah, so I think that's something that's very, very important. So remember, so a lot of energy is needed to overcome the hydrogen bonds and therefore allow the molecules to escape, to form a what? To form a gas. That's if we are talking about liquid water, right? Okay, so that's very important. So you're wondering, then why is that point important with regards to life? So it's important because imagine if water had a very, very low boiling point. So you can imagine you are walking, and then it gets really, really hot, and then steam starts coming out of your mouth, of your ears, your nose. That wouldn't be helpful now, would it? No, it definitely wouldn't be, right? And it could, yeah, and you can imagine just how easily dehydrated we could be. Okay, we could easily be becoming dehydrated. Cells could be drying up. I'm sure you've learned about when a cell loses too much water, it dies off like that, right? So again, all those things would have been happening. And remember, we said many biochemical reactions. So meaning many reactions, chemical reactions which occur in our cells, use water as a medium, right? Or in short, they take place in water. So what this basically means is if that water is easily being lost, the water levels are decreasing, right? And if the water levels are decreasing, then what are we having? Then we are going to have a lot of derangements in our we are going to have a lot of derangements in our reactions. Okay, so that's something that's an important point to take note of. So I think there's someone that wants to join. Let me just admit them. Yeah, so that's something that's important about these properties. So now let's now talk about water and temperature. So another important thing about water is its ability to resist temperature changes. So water is and again, this just marries with the previous point that I'm from talking about, where water is got a good ability to what to resist temperature changes. Just for instance, just look at methylated spirit, right? Like you just remove it out of the bottle and it vaporizes. But for water, look at just how long it takes for your tea to be ready. It takes a long time for your cup of tea to be ready, right? Or for your water to bath to be ready. So it takes time for you to what to heat water. And also just look at how long it takes for your cup of tea to cool. Sometimes we even have to add cool water or cold water, right? Just so that you can be able to take your tea. So this is a very very important property of water, and we'll talk about it in a short while. As yeah, so it no it re- it re- a lot of energy, a lot of heat energy is required to raise the temperature of water, and this is because of what? This is because water has got a high specific heat capacity. Okay, and so in as much as it takes a lot of heat energy to raise the temperature of water, again it takes water to lose a lot of heat energy to lower its temperature. Like I gave the example about the cup of tea. You make a cup of tea, and sometimes you may have to pour cold water, or cool water, for instance, just to ensure that your cup of tea is to a point which you can easily consumed, right? So again, that's something that's important. So liquid water does not easily heat up or cool down. So again, that's very very important. So now you may be wondering then, how does water do this, and how is this important to our lives? So that's what we'll be looking at. Okay, so because it's got a high specific heat capacity, it means that it takes a lot of energy to raise the temperature of 1 kg of water by 1 degree Celsius. Okay, and also a lot of energy has to be given out before the temperature of 1 kg of water falls by 1 degree Celsius of temperature. So again, that's just something that we've been talking about. Okay, so again, maybe you're wondering what's the reason. Again, hydrogen bonding. So when energy is supplied to a substance, right? So let's say you are trying to heat, let's say, water or any particular substance, the molecules will begin. You're going to give those molecules kinetic energy. Remember, in thermochemistry, yesterday we discussed that the law of conservation says that energy in the universe is constant, right? So no energy is created, no energy is destroyed. It just changes the forms. So when you are heating a substance, what's practically happening is that that heat energy is being converted to what? To the kinetic energy of the what? Of those molecules. And what's going to happen is that the temperature of that substance will rise. Now, what happens with water is that as you are applying that heat energy, some of the energy goes into the hydrogen bonds, okay, and only part of the energy goes into increasing the temperature of the liquid. So first of all, what's happening is, remember, we know that the molecules need to have an increase in what? In kinetic energy. But then not all the energy, not all the heat energy that you are supplying goes into increasing the kinetic energy of these molecules. And remember, for the temperature to rise, the kinetic energy of the molecules has to rise. But because water has hydrogen bonding, or has hydrogen bonds between its molecules, part of the energy that you are supplying, the heat energy you are supplying, has to go into the what? The breaking of the hydrogen bonds. So remember, the hydrogen bonds are holding the water molecules together. So part of the energy goes into what? Into breaking the bonds, and only part of the energy goes into what? Into increasing the kinetic energy and therefore raising the temperature. Therefore, it's going to require a lot of energy to raise the temperature of what? Of 1 kg of water by 1 degree Celsius, which is what? A high specific heat capacity. Another way to think of this, imagine you are heating something using 40 joules. Huh? So you are heating using 40 joules, you are putting 40 joules into a particular substance, okay? And all that 40 joules goes into increasing the kinetic energy of your molecules, and the temperature rises. But then when you come to water, because of the hydrogen bonds, that 40 joules gets split maybe into half. So the 20 joules goes into increasing the what? Into increasing the temperature by increasing the kinetic energy of the molecules, and then half 20 joules goes into breaking the what? Breaking the hydrogen bond. So what then happens? What then happens is that you are going to get a lower temperature rise as compared to that substance which doesn't have the what? The hydrogen bonds. So you can see the difference there between certain substances. So you got alcohol or ethanol, you see it's zero point 0.6. So you see iron has got a specific heat capacity of zero point 0.1. So you see that water really is very, very interesting, as we could see from these things. And we'll talk about how this is very, very important with regards to supporting life. Huh? With regards to supporting life. So we want to talk about something, a calorie. So a calorie is the amount of heat that will raise the temperature of 1 gram of water by 1 degrees. Huh? So we've talked about specific heat capacity of water. So in comparison with alcohol, we see that water has got a very, very high specific heat capacity for its size. Okay, and to put it into perspective, it has got a 10 times high specific heat capacity than iron. I think that's interesting. So, and then the specific heat of what again is due to the what? To the hydrogen bonding. I think I've really, really explained this point. So, yeah, so that's what that paragraph is explaining. So now, remember, this is biology, and the key thing is for us to be able to learn this and be able to understand the consequences or the reason and the importance for that with regards to what? With regards to supporting life, isn't it? So what does this mean? This means that the temperature of water will rise slower than the temperature of almost any other material. So now let me put this into perspective. So what this basically means is that you can just try to imagine if our body, if our, if the temperatures of water, or if the temperature of water would easily rise up. Imagine what could have been happening to our body temperatures in October. We would be freezing in June or in winter, all right? So we would be freezing in winter. And also, when it comes to October or to the summer season, what would be happening? We would be boiling. Okay, we would be boiling, right? Because the temperature of water would have been what? Increasing so much. You learn in physiology next year that a large portion of your body is water. It's water. Okay, so because water's temperature doesn't change anyhow, this is very, very important because it enables our what? Our body temperatures to be maintained. And because our body temperatures is going to be maintained within a certain range, this is important because remember, enzymes, as we will learn later on, is that enzymes are what? Are destroyed by high temperatures, isn't it? So imagine if you are walking and then your body temperature goes to 45 degrees Celsius because it's summer. You die. Oh, sorry. But yeah, the person can die, right? So the person can die. So because the enzymes are denatured, and so biochemical reactions are what are not occurring. So that's something that's very, very important. So with regards to life, this is important because it also helps to what to maintain our body temperatures. So that's why whether it's hot, whether it's cold, when you measure your body temperatures, it will be relatively around the same range, isn't it? 36.1, 36.5, it will be around that range. The reason being is because the temperature of water doesn't change rapidly. So it's relatively what constant. And so it's that which is very, very important. And that's why it takes a long time for someone to die when exposed to extreme temperatures, either too hot or too cold. It takes long for someone to die. Okay, so that's an important point to take note of. Then also the high water content of plants and animals helps them to maintain a relatively constant internal temperature. So you talked about about homeostasis in grade 12, where the body maintains itself, maintains its properties. So water is very important in maintaining our body temperature. Okay, and our internal body temperature, that is to say, yeah, our internal temperature. Okay. Then, so that's about that. So now we now talk about vaporization or latent heat of vaporization. So when it comes to latent heat of vaporization, you are talking about how much energy does a particular 1 kg of a substance require for it to be vaporized. Okay, so a lot of heat energy is needed to evaporate water, right, or to vaporize water. And and one thing that is very, very important about when water evaporates is that when it evaporates or it leaves a surface, is that it draws in heat energy out of the material underneath, therefore creating a cooling effect. Here's the thing. Perhaps you've had those instances where you've walked in the sun for a long time and then you are feeling all hot, you are sweating, and then, like, when I just reach, I'll just go direct into the shower because I'm feeling so hot. Then when you reach home, you decide to sit down, and and then the sweat vaporizes, and you stop feeling as hot as you were feeling. Say, you know what, I think I'll even bath maybe after an hour. Why has that happened? Because when water vaporizes from a surface, it's got a cooling effect. And don't worry, we'll explain how this happens. Okay, so vaporization or evaporation, like we talked about, is just the change from of physical state from a liquid to a gas, and water has a high latent heat of vaporization. So it simply means that for you to vaporize water, you need a lot of heat energy. Okay, so again, hydrogen bonding is very important, and it's actually the reason for this property as well. So remember, in order for a water molecule to break from its fellow water molecules, sorry about that. So the hydrogen bonds have to be broken, right? But what happens is that, remember, for you to vaporize water, you remember, like what I said, you have to increase the distances what between the molecules so that they can change from what from the liquid to the gaseous phase. So as this is happening, yeah, so as this is happening, it takes energy to increase the distances between these water molecules, isn't it? And so what you need is the heat energy. Now, because water has got hydrogen bonds, a lot of energy, heat energy, is going to go into breaking the hydrogen bonds. Okay, because the water molecules are being held together by what? By the hydrogen bonds. So if you are to separate them, into gaseous state, the hydrogen bonds have to be broken. So because this will require a lot of heat energy, what's going to happen is, because that surface, okay, so to think of our skin when you are sweating, there is a lot of heat that's on your skin. So that sweat which is on your skin, due to the heat that's on your skin, is going to what? To break the hydrogen bonds. And then the water is going to what? To vaporize. So your sweat is going to vaporize, but because it required a lot of heat energy, meaning that your skin, remember, energy is never lost. So energy has just been transferred from what? From heat energy into your skin to the energy used to break the hydrogen bonds. And so as a result, what's going to happen is that your skin loses that energy because the energy has been transferred into what? Into the breaking of hydrogen bonds in the water. Therefore, as water evaporates from the surface of your skin, the escaping molecules will carry a lot of energy with them, and as a result you're going to have a cooling effect. Okay, you are going to have a cooling effect. That's why they say if you are not sweating, you can overheat. Your body can overheat. Okay, because sweating is very, very important. So evaporation from the surface of a plant or animal is one of the principal ways in which organisms have evolved a mechanism of lowering their body temperatures. So like for humans, for mammals, we sweat. So when you sweat, like I explained, you are going to feel relatively warmer. Okay, so now we now talk about density and freezing properties of water. So I hope you've seen uh, how the hydrogen bonds work in the vaporization, and also the biological relevance of what we've discussed, right? Because everything that we are discussing, remember, this is biology, right? So we are centering everything on mm, on how does it affect what? How does it affect life of that particular organism, right? So now let's now talk about density and freezing properties of water. I think we all have had experiences where you get, or rather, when you get water and put it in a bottle and you put it in the freezer, and after some time, you know, the water expands, and if the bottle was a plastic bottle, a plastic container, it even rips open that container. So what has happened there? So one thing for sure, we know that the mass of the water hasn't changed. Okay, so the mass of the water hasn't changed. So then what has changed? So what has changed there is what? It's just the volume. Because remember, for the water to expand and rip open that container or cause a bulging in that container in which you had placed it, it's a change in what? A volume. Huh? So it means that there's been an increase in the volume of the of the water. And that's now what's causing what has been seen, or what you may see happening there. So that's something important to take note of. Now, since the okay, you can say the weight or the mass. So since the mass of the water is the same, but the volume has changed, what happens to the density? That's how to think about. So don't think which one has got the higher density. Just look at it like this, right? So density is what? Density is equals to mass over volume. So if the mass remains the same and then the volume increases, what does this tell us? Remember, every time you've got a formula and you are increasing the denominator, just know that the value of what you're trying to solve for is decreasing. So the same thing for density. Density is equals to mass over volume. When you increase the volume, the density decreases, right? So that's what's going to happen. So that's why liquid water has got a higher density than what? Than ice. Okay, I hope that's been done and dealt with. So why is it then that this is observed? And of course, we are going to talk about what's the relevance of this with regards to survival as organisms, right? And most especially as for aquatic organisms, especially. So at 0 degrees, what's happening? The ice, when you look at ice looks crystalline. Huh? So by crystalline, I mean when you look at ice, it tends to have some shape. Okay, it can be like a cube, it can be one. But one thing about that, it's going to have a certain regular, no, it will not be regular per se, but it's just going to have a certain arrangement which is going to be unique. So, but when you go deeper to see the molecules, you're going to realize that the molecules of water in that particular ice, are arranged in a regular hexagonal crystalline network. So, okay, so let me just explain that. It simply means that the water molecules are not arranged in a disorganized manner. No, they are organized in a very, very regular manner. That crystalline there is just to say it arranges itself as though it's a crystal. So the water molecules are in order. And which order is this? Remember, I said each water molecule can be hydrogen bonded to up to four other water molecules. So you've got one water molecule and it's surrounded by other water molecules joined by hydrogen bonds. So because this water is this ice rather, so because this ice is made up of water molecules which are are bonded to one another by hydrogen bonds, that hydrogen bond will have a certain distance, okay, that it will be creating between the water molecules, isn't it? So there will be that distance that hydrogen bonding will be creating between those molecules, right? I hope that's clear. Now, as the temperature increases above 0 degrees, once you go above 1 degrees, you see that the water, or rather the ice, so the ice begins to melt. So what happens when the melting is taking place? What's happening? Temperature is increasing, right? And what happens when temperature increases? Some of the hydrogen bonds begin to get broken. So now, as these hydrogen bonds are being broken, it means that these water molecules, which were arranged in a nice crystalline, regular hexagonal network, they are now all over the place, right? They are clustered, 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 and they are more compact. So by compact, I mean they are closely together. Okay, they are closely together, right? So now what happens is that because they are more closely together as compared to those water molecules which were well spaced out in ice, so you see that what has happened, since they've become more compact, you see that their volume decreases. Uh, a good example in which you can picture this is this. Look at how eggs on a tray are, right? You find that when you put eggs on a tray, they are going to occupy a large space, right? A very large space. But if you get the same eggs, you put them in a plastic, you tie the plastic, you see that they're just going to occupy a very small amount of space. Why is it that? Because their arrangement, when you put them in a plastic, they are more compact than when you put them on a tray. So because of that, you see that the volume, the space that they're occupying is less. Okay, so I hope that helps. So now, meaning that when we now talk about the volume, so that's why the volume of liquid water is less than the volume of ice. So remember, density is what? Is mass over volume. So because of that, like I explained, because the volume for ice is higher, so that's why liquid water is denser than ice. So I hope that really does it. So now, why is this important? So what this, and then you also want to know at which temperature is water the most dense. So water is most dense at what? At 4 degrees Celsius, okay? So yeah, so water is most dense at 4 degrees Celsius. So you may now want to ask to say, okay, how does this really relate to biology? Yeah, like how does this really, or everything that we've discussed, how does it relate to biology? Well, it relates to biology in the sense that when you look at a fish pond, or maybe those that have watched maybe movies, cartoons, is it Ice Age? Like that cartoon, huh? Anyway, but you always see that whenever they are showing it can be a fish pond, it can be an ocean, or it can be the Arctic. If they are showing anything that has any water body that has that has frozen, you see that the ice is not under. The ice is always going to be what? Is always going to be on top. All right. So why is that important and why does it happen? So why that happens, first of all, it's because we know that the more the water gets cooler, it's going to be what? The less dense it is, right? And when the temperature reaches at 4 degrees Celsius, then that's when water will be the most dense. And what do we know about something that is dense? Something that's dense goes what? Goes down, down, down. Okay, so something that dense is going to go down, 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 and down, down. So the most dense thing is going to be under, followed by the what's more dense than the others, just like that, right? And so ice, which is the least dense, is going to be what? It's going to be on top. So why is this important? It is very important because it means that when a place is very cold, the all the water that is very very cold is going to go on top, and then the most warm water will go to the surface, followed by the one that's a little bit warm, just like that, until in case ice forms, it's going to be on top. So now, how does this protect aquatic organisms that live in water? It's simply this: even if a pond or a water body is frozen on top, organisms such as fish, bacteria, and other aquatic animals organisms can still live under, because the temperature that is under, first of all, it is relatively warm and it remains to be liquid. You can imagine if it was the other way around, where an ocean begins to become ice from the bottom going up. That would be catastrophic, because it means the bottom would have been ice first, then the top is where you have liquid, or it's where you've got the most warm water. So you see, life would have been hard, right? But with the way it is, the top can be ice, but you see organisms under enjoying and living life. So that's where really that comes in. Huh? Okay, so the last point for today, we'll talk about cohesion and adhesion of water molecules. So this is very, very important with regards to this. So first of all, we want to understand what is adhesion, what is cohesion. So co. Every time you see cooperation, commitment, coordination. So it usually talks about similar things, right? Let's cooperate. So you are trying to what? Cooperate. Huh? So you are trying to, you've got a similar agenda, you've got the same agenda. So cohesion, just yeah, so that's how you can think of. So cohesion, okay? So cohesion is just the attraction between molecules of similar substances, okay? So you've got water and water, they attract, so you've got cohesion there. So the hydrogen bonding gives water considerable cohesive properties. So again, it comes where on the hydrogen bond. So everything that we are going to talk about, the properties of water, they come from the hydrogen bonds, the hydrogen bonds, the hydrogen bonds. So that's why they wanted you to start your biology with what? With some a little bit of chemistry, so that you can be able to appreciate all these things. Huh? So that's why we started with the atomic structure, so that you can be able to appreciate this biology. Yeah? So again, so we look at that, right? So hydrogen bonding gives considerable cohesive properties. So uh, how does this cohesion occur? We've talked about the water molecules of what stick together as a result of what? As a result of polarity. What's that polarity? Remember, because of the differences in the electronegativities between the hydrogen and the oxygen. So the oxygen is slightly negative, the hydrogen is slightly positive. So as a result of that, those opposite sides of different water molecules can interact, and so there is the cohesion property, right? So we talk about why that's important to life. let me now talk about adhesion. So adhesion, this is the attraction what you know, between molecules of different substances. So this is where water molecules are able to stick to surfaces of let's say a glass container. Who has ever drunk water and they sipped all the water molecules from the cup? It's hard, right? Exactly, because water molecules have got the ability to stick to what? To stick to other surfaces. Okay? So you may be wondering, really, why is this important? So first let's talk about cohesion, since that's what we started with. So cohesion of water is responsible for what we call the surface tension. So what happens? So basically, when you're talking about surface tension, like the word it tells, so you're talking about the surface of of something and how tense it is. Okay. Have you ever? Let me give an example of maybe a drum, huh? So like those drums that people beat and everything. Or yeah, you find that there's 10 times where they have to tune them, right? Sometimes you can make them loose and that will change the sound, isn't it? But there are times where you can make the drum to be so tense, like that thing that's on the drum. Like you can make it to be so tense. Okay? So by tense it's simply it's going to be so, what can I say, relatively hard, right? It's going to be relatively hard. And so at an air water interface, so what they are now talking about is, if let's say we talk about about a pond, so a pond will always have an air water interface. So what is air water interface? An air water interface simply is a point where on top you've got air and down you've got what? You've got water. So on top of the pond, there are water molecules, and then above the pond, there are air molecules, isn't it? So that's an interface. Okay. Now there are certain interactions that are happening around those points, and especially those water molecules that are on the surface. Okay, because what's happening with these water molecules is that they are interacting where, remember we said one water molecule can accommodate how many? Four other water molecules, right? By hydrogen bonding. So what this basically means is that now that particular water molecule, so let's just think of one particular water molecule. So one water molecule that that's on the top surface, right? It's being on the left, it's being attached to a water molecule. On the right, it's attached by a water molecule. Downwards, it's interacting with the water molecule. But on top, there's no water molecule. Why? Because on top, there are air molecules. Okay? Because this is a water molecule that's on the surface, isn't it? So, what then happens is that because of this, it's like those surface water molecules are tensed. It's like they are being pulled downwards and on the sides, but there is nothing on top to which they are attached to. So at the end of the day, because of this unequal distribution of hydrogen bonds, there's going to be a surface tension, because all of the hydrogen bonds in water, just like I've explained, uh, there are hydrogen bonds downwards and also on the surfaces. So they are going to cause water molecules to form more or less like something like an elastic skin. But of course, this is not a skin, right? But it's just going to form a tense surface, because it's like let me give an example. It's like you've got, maybe let's say you've got people are holding hands, right? Yeah, like people, let's say two people are holding hands, and then yeah, so these people are holding hands, you and then you drop something at the point at where they are holding hands. You find that they will be able to accommodate that thing that has been dropped. So why is it occurring? It's because at this point there are forces which are actually acting where sideways, right? But also for the water molecules, there's also that water molecule on the surface is being put on the left, on the right, and also where downwards. Okay, so as a result of this, there is that tenseness that is there, and as a result, you'd find that some aquatic organisms. I'm sure we've seen some maybe on National Geographic Channel, on Animal Planet. They will show some small insects which are able to walk on water, right? So they're able to walk on water because what? Because of surface tension. And it's as a result of what? Hydrogen bonding. But these hydrogen bonds are what? Are unequally distributed because the hydrogen bonds on the left, on the right, and under that surface water molecule, but nothing on top. So because of that, it creates a what? A tense surface. Okay, so cohesion of liquid of water as a result is responsible for its surface tension. So why are they saying it's the cohesion of water? Because the surface tension is a result of the hydrogen bonds between the between the water molecules, which are the similar molecules, right? So cohesion, water molecule on the left, right, and down, but nothing on top. So creates a what? A surface that is tense. And water has got a higher surface tension than other liquids, of course, because of what? Because of hydrogen bonding, right? Okay, so okay, yeah, okay, so we should be starting carbohydrates. Most okay, anyway, most likely tomorrow. Yeah, so let's just finish this part, and then we can go to the next thing before 22. Yeah, our we will make up for the other for the others. Okay, tomorrow. So the adhesion of liquid water to other substances such as glass is responsible for capillary action. So we are done talking about cohesion, right? And how it causes surface tension. So before we can proceed, is there a question on cohesion of water and how it results into surface tension? Okay, so okay. So if there are no questions, so let's now talk about the adhesion of water. So, like we said, adhesion is between different substances, right? So, what happens for the adhesion of water? So, what you are looking at basically, it's you know water with something else, right? Remember, it's different substances, right? So, for instance, let's talk of water and what and glass. Remember, I gave an example. Say, who has ever drank water from a cup and they sipped out all the water uh, molecules? I bet no one, right? Because there is that adhesion. So now it's responsible for something called capillary action. So I don't know whether your syllabus still has plant physiology, but for us, we used to learn about plant physiology where we talk about how water is able to rise in a very, very tall tree. I'm sure you may have wondered to say, but how does water move up a very, very long tree? Well, your answer is here. It's all about what? It's all about adhesion of water molecules, which causes this the capillary action. So now this experiment which is done here is basically to help you appreciate this particular principle. So let me see if I can get us to write something. So this example is like this, right? So if you've got a beaker, so what I'm drawing, that's a beaker, right? So if you've got a beaker and it's containing water, right? So just imagine this yellow thing that I've drawn, that's a beaker, right? And so it's containing water. Then what then you do is that you get a narrow tube. Okay, so then you now place a narrow tube. Okay, so let's do this. Let's raise it up a bit so that we can be able to appreciate. So now then we put in a what? A glass tube with a narrow diameter. So we put in something like that, and we put in something like that, right? So remember, here there is what? Here there is water. Now, what's going to happen is that the water in the tube, okay, so if we've gotten a narrow tube, the one that I've drawn there, we place it in a beaker. So this beaker that I drew has got water in it, right? And then we get a glass tube with a narrow diameter, which is a glass tube with a diameter smaller than that of the beaker, right? So what's going to happen is that the water will rise in the tube, which is in the glass tube, above the level of water in the what? In the beaker, because the adhesion of water to the glass surface, drawing it upward, is stronger than the force of gravity drawing it down. So what basically is happening is that you're going to find that in this beaker, you would find that the water level, okay, so you'd find that the water level, so you're going to find that, okay, I don't know why, okay, yeah, so you're going to find that the water level, maybe at this point, will be at, okay, I don't know why we're having difficulty, but yeah, so we're having, yeah, that water level, right? But what, so all that I'm drawing is water levels, right? But you find that in this narrow tube, it can even go above what is what is in the what is in the rest of what's in the rest of the larger beaker. Why? Because of the adhesion of water molecules to the what? To the glass surfaces, right? And so what's happening that the water that is in this small narrow tube, the effect of gravity is less, because the narrower something is, uh the better the adhesion. Because here is the catch. So you can just follow my pointer there, right? So you can, I hope everyone is able to see my pointer. So you see, if, so my pointer is on the left, right? So if you've got at this particular point where you've got an adhesion force, and then here again you've got an adhesion force. This force, yes, is an important force, but because of the distance that is between the left and the right points, you see that this particular force will not have so much effect, because the distance between the 2 points are just too large, isn't it? Or rather, the distance is too much, and so you find that the effect of the adhesion forces, we may not even get to what, to appreciate them. But then when we come to this narrow one, because it's a narrow tube, right? So you find that the adhesion forces which are occurring on the sides of this narrow tube, they are going to be relatively greater. Why are they greater? Because the tube is small, the force of gravity which is occurring is going to be what, is going to be very, very small, relative, okay, relative to the what, to the adhesion. So the adhesion, the forces which will be occurring on the sides of that narrow tube, they are going to be stronger, and as a result, the water level can rise in that narrow tube above the level of water in the beaker. Okay, and it is this property of water that allows high trees to transport water from their roots to their leaves. So like I said, in case you were wondering to say, but how is it that these plants are able to carry water up their leaves from their roots? So they use the word capillary action. So capillarity is very, very important. So that's basically about it. So of course we've already talked about polarity, which is an uneven charge distribution within a molecule. So in water we've talked about it, where the oxygen part is slightly negative and the hydrogen parts are slightly positive. So tomorrow we start talking about these organic molecules. So we talk about carbohydrates, lipids, proteins, enzymes. So that's where we go to. So otherwise, that's pretty much about it. Are there any questions?